Okay. So hello everyone. So welcome to attend our this week Rutgers Efficient AI seminar talk. So today we're very glad that we have the Dr. Amir Gholami from the UC Berkeley to give us the talk. And Amir is a senior research fellow at ICSI and Berkeley AI Research. He received his PhD from the UT Austin, and his PhD dissertation received the Austin Best Dissertation Award in 2018. He is also a Melosh Medal finalist, the recipient of the Best Student Award in SC 2017, gold medal in the ACM Student Research Competition, as well as Best Student Paper finalist in SC 14. And Amir was also part of the NVIDIA team that for the first time made low precision neural training possible, enabling more than 10 times increase in computer power through tensor cores. So that technology has been widely adopted in GPUs today. So Amir's current research focuses on efficient AI at the edge and the scalable training of the neural models. So now let's welcome Amir, give us this very wonderful talk.
Thanks so much, Bo, for having me. It's a great honor to be giving this talk at Rutgers University, and thanks so much for everyone who's joining. Please feel free to ask questions in the middle of the talk if there was anything that was not clear. So this is a joint work with many people in our lab, as you can see. So I'll be presenting on behalf of many people, as well as our collaborators at Amazon. Part of this project, specifically Hawk V3, was performed in collaboration with Amazon. And today, mainly I'll talk about neural network quantization. If there was time, we're also going to talk about pruning, which is a special case of quantization with 0 bits. So let's basically give, just get started with some background information. As many of you know, the cost of training and deploying neural networks has been exponentially increasing. And so this is not just because we have, some companies like to train very big models like GPT-3. It's actually because some of the new neural network models, such as Transformers, are actually getting much better performance, which is critical for applications such as autonomous driving. We want to have as high accuracy as possible when we're detecting a pedestrian in front of the car. And many of these models require much more compute, both to train as well as to deploy. So this is a data that we created. OpenAI had a similar result of AI and compute, where they were looking mostly in reinforcement learning based models. We thought, okay, let's look at what's going on when we're looking at computer vision and NLP and speech. Let's see how is the compute changing in time. And this is the state-of-the-art models that we're plotting here, where you can see different models, starting from AlexNet, ResNet 50, DenseNet, and so forth. Throughout different years, what is the training compute needed to train these models? And as you can see, this is exponentially increasing even for CV. So 15x, even without transformers. But when we're looking at the transformer models, the amount of compute needed to train these models has been increasing by a factor of 700x every 2 years. And in computer vision, the recent approach of using self-supervised learning has a similar flavor. You have a lot of data, unlabeled data. You can train, for example, for 1,000 epochs to get better performance sometimes than supervised learning. And so both the model and amount of data has been exponentially increasing. On the other hand, it's not just about compute. If you look at the memory footprint and the number of parameters for several of these models, that's also exponentially increasing. So specifically for the transformer models, we see that the number of parameters of these models, not the flops, the number of parameters has been increasing exponentially as well. So starting from late 2017, when we had the transformer paper, all the way to Albert, Electra, GPT-3, and G-Shard, we're seeing an exponential growth in the state-of-the-art models. And importantly, the hardware that we have has not been able to keep up with this. If you look at the scaling for hardware's peak flops, so this is essentially normalized scaling. The black line shows the different processors that we've had over the years, starting from the R10,000 startup, which was used to train MNIST, all the way to A100. You can see that the peak flops of this hardware, the peak computational power of the hardware, has been only scaling by a factor of 3x every 2 years, and only 1.4x for the bandwidth of these processors. So in terms of memory bandwidth, it's even slower. So it's nothing compared to the 15x of compute for computer vision, or 700x compute for transformer models, or the memory footprint. So we really need to think out of the box. If you want to deploy these neural networks in latency critical applications where we need the result within a threshold. For example, in autonomous driving, you need to detect whether there is a pedestrian in front of you or not at most at 100 milliseconds so that the car can take action in real time. Or other applications such as, for example, AR, VR, if the latency is too high, it's going to create a headache for the customer, right? So you need to have low latency and high accuracy for many of these applications. And even server-grade hardware, such as Ampere A100, is not able to provide a solution. So we actually need to rethink the way we are designing these models if you want to be able to surpass this challenge. So one of the things that people have been doing over the past decade has been to design as big and sometimes as inefficient model as possible, forget about efficiency, and see if we can actually capture better accuracy, if we can capture better semantic features from an image, or better, encode better information from natural language. Now we have surpassed a lot of, in a lot of cases, we have surpassed human level performance. And now the next challenge in this decade, what we're predicting is the efficient deployment of these for cases where you have latency requirements, such as autonomous driving, or cases such as AR, VR, which we just discussed. And that really requires that we rethink the way we're designing, training, and deploying these models. And this is essentially a complete process that you need to deploy this on a target hardware and come back and redesign your neural network. So for example, let's say Bo starts a new AI company, startups, he's hiring us, for a new task, let's say. And obviously for that new task, most probably it's not ImageNet. Let's say it's a new neural network that we need to design. So we need to rethink, are we going to use ResNet 50, or maybe we are using DenseNet or EfficientNet? Probably none of these. We need to change the neural net architecture. So let's say we sample a few neural network architectures, we do the training, and then we deploy this on a target hardware, and we see that the latency is, for example, 500 milliseconds instead of 100 milliseconds. We need to go back all the way to the neural net design, change the neural net, maybe change the depth, maybe change the width, so that we can get the accuracy and be still under this 100 millisecond. Obviously, at scale, we cannot do this manually. So there is a lot of work integrating this design, training, and deployment such that you can design a neural network systematically and deploy it within the application-specific thresholds. And one of the issues here is essentially when you're deploying these models, you need to perform things such as quantization or pruning to make the model more efficient. And many of the existing methods for these two phases are not automated. So the majority of today's talk will be about automating and finding systematic methods that can provide you with efficient models so that you don't need to do hand tuning for this part. And if this piece of the puzzle is automated, then you can think of designing a NAS algorithm that would combine this whole ecosystem and would design an efficient neural network for a particular task. So let's get started with quantization. And if there was time, I'll share some of our results about pruning with you. So quantization has been, there's a lot of different methods for making neural networks efficient when you're deploying them. And one of the most promising ones is quantization. So quantization is a very simple process. Basically, you have a tensor, for example, here 0.34, for your convolution, or 3.75. It's like assume a 3x3 convolution, and you want to represent this tensor. Instead of using floating point values, for example, you want to represent this with 100. You want to represent this with 250. For example, to represent this with 70. If you have integer values when we're representing this tensor or convolution, then when we're performing the convolution operation, we can utilize low precision logic, and we can get 4 to 8x speed up when we're doing the convolution. And so how can we do this quantization? It's a very simple function. You have your real values. Let's say, for example, 5.64 is here. You want to map this to an integer. Essentially, you want to map this, for example, to the value of 70, and so forth. Another real value will be mapped to these integers. Essentially, the operation that you're doing is very, very simple partitioning. You have your real value, say 5.64. You know how many partitions you have. Let's say you're using 8-bit precision, which has 256 buckets. So you know that this partition size is essentially the range of your parameters 12 divided by 256, because the range is, for example, from -5 to 7. And then you divide this 5.64 with the scale, you round the results, and you get your integer value. And if you want to, for example, make sure that 0 is exactly represented, so that 0 exactly perfectly maps to 0, you add this 0 point. So the operation is very simple. I have a floating point value. I divide it by the number of partitions that I have. I round the result, and then I make sure that the 0 point is exactly represented. And that gives me the, for example, 7 is the value of 70 here. Now, why do we want to do this? If you look at how hardware is executing arithmetic, you'll see that the majority of the cost comes from loading data from DRAM. So this is a result from Professor Horowitz at Stanford, which is a very well-cited result here, that's reporting the energy associated with performing different types of operations. For example, if you're performing a 32-bit DRAM read, you're essentially just reading 32-bit data from DRAM. What's the associated energy that you have to pay? Well, it's about 600 picojoules. If we then compare what's the cost of performing a multiplication with 8-bit precision, you see that that's significantly smaller, 4 orders of magnitude smaller. And interestingly, if you see the majority of the problems we have, especially at the edge and even at the data center, is the power requirement for deploying some of these neural net applications. And if you're performing quantization, it means that instead of reading 32-bit data, you're reading 8-bit data. That's much more efficient. So you're not paying this 600 picojoule energy. You're paying exponentially smaller energy for doing this read. And then the other thing is that it's not only about energy. You can also utilize lower precision logic so that you can get better speed up. And the reason for that is that if you compare a multiplier that's 32-bit with 8-bit, let's say you have a multiplier in your logic that multiplies two 32-bit numbers, and you have another multiplier that does 8-bit multiplication, you'll see that the 32-bit multiplier occupies 3,400 micrometer square of your die area, whereas an 8-bit multiplier is about 15x smaller. So if I only needed to perform 8-bit multiplications, I can put a lot more reduced precision logic. And so my logic can be fast, which is quite intuitive. So quantization is going to reduce two important things for us. First is the energy cost. Second is that because the area required for performing smaller bit precision multiplication is smaller, is more efficient, we can get speed up when we're doing quantization. And this is completely intuitive. This is a result from NVIDIA's RTX system, where if you're performing a tensor operation with FP16, you get, for example, 8x throughput compared to their floating point counterpart in Pascal. If you're performing int8 tensor operations, you get a factor of 2 speed up over FP16. And if you're performing int4, you get another factor of 2. So just going to int4 compared to FP16 is going to get a theoretical speed up of 4x. And it diminishes the energy cost as well. So that's why we want to perform low bit precision for inference. And we've been doing this for training as well. So before FP16, we were always performing training with FP32. And when we started using FP16 or tensor cores, that's when we got a factor of 10x speed up when we were doing training. Unfortunately, for training, it has been very difficult to go to int8 and int4. So there's a lot of fundamental problems there, especially with vanishing gradient. But for inference, once you have trained the network and you have a trained network in your hand, you can perform inference with lower bit precision. So let's actually take a look and see how this is performed. So in our neural network, we have an input X, and we're performing different operations, for example, fully connected or convolution. So let's take, for example, let's say you're doing one of these, Y equals W times X. And let's say this is your W matrix and this is your X matrix. When you're doing this in floating point, we know how to do this. It's simple matrix multiplication. But when we are doing this in quantized precision, it's a very, very simple operation. For W, instead of representing it with floating point value, we're representing it with integer values, quantized values, but it has a common scale that we need to take care of. So there's a scale multiplied by this. And same thing for X and same thing for Y. So let's see how we can perform this simple multiplication when we have quantized values for W and X instead of floating point. Well, it's very simple. For simplicity, let's assume that we don't need to worry about this 0 point. Just, it's the same, but without loss of generality, let's assume that the 0 point is 0, and we're doing symmetric quantization. This means that when I have the convolution, the 3x3 convolution, or my fully connected, instead of representing the values with floating point, I'm representing them with integer values, let's say 4-bit. And I'm scaling, I'm factoring out a scale, so a common scale for all of these W, which could be a floating point, which could be a rational number. It's essentially just this common scalar. And same thing for my X. X is also integer times the scale, and output will also be an integer times the scale. So how do we perform this multiplication? It's pretty simple. We first multiply X and W together in 4-bit precision. We accumulate the results in 32-bit precision. For example, let's say this was 4, 120, let's say 3, and these values were, 4, 1 and 2, right? So basically what I'm performing is I'm multiplying 4 by 4 plus 120 times 1 plus 3 times 2, and I'm accumulating them in 32 precision so that I don't lose results. And then once I have this in32 result, what I need to do is essentially take into account that these had a scale that I did a multiply beforehand. So I did a multiply SX, I can multiply that now, multiply SW, the factor for W, and then my output will also have a factor. So I take that into account and I perform a rounding operation, and that gives me the output. So is this clear? If there's any questions here, please let me know. So this is pretty straightforward, and this is known as integer only or fixed point or dyadic quantization, but not all quantization algorithms use this approach. So in fact, if you look at almost all of the literature in quantization, the majority of it, including some of our papers, was using simulated quantization, or some people also call it fake quantization. So the way that this works is the following. You have your W is in int4 precision. So you have your WI4 and you have your XI4. It's essentially stored in 4-bit precision. But when you're performing the arithmetic in hardware, you're doing the multiplication and accumulation in FP32 logic. So when I'm multiplying these together, I'm not multiplying WI4 and XI4 in integer arithmetic. I'm multiplying them in floating point arithmetic. And then once I'm done with the floating point arithmetic, then only at the end, I perform the quantization back to get YI4. Well, this is okay if you only want to reduce the memory footprint of your model. For example, if you want to reduce GPT-3 from 175 billion times FP16, it's basically about 350 gigabyte. If you want to reduce the model footprint, that's okay. But if you're doing the logic in FP32, you're not going to get the speed up. And in fact, it's not just about that. It's not as simple as just performing this in integer operation. The reason many people were doing this was because quantizing a few of the components of the neural network with integer only would lead to accuracy degradation. So for example, a lot of the works keep the batch normalization parameters in floating point logic. So if you look at the batch norm, the statistics are kept at floating point, because if you're quantizing them, you lose accuracy. Or the residual connection, even for some binary neural networks, some people do residual connection in FP32, which is not really good because it really kills the performance when you're executing this in hardware. But people do this because if you're quantizing this, it leads to bad results table. So that's why usually people don't do this. But the problem is, there has been this notion that if you're performing the simulated quantization, it's okay. You can deploy this on tensor cores and you're going to get the results. But in fact, that's not the case. And so let's just take into consideration what happens when you're performing floating point logic for residual connection versus integer only logic. This can lead to order 1 discrepancy. So when I present this, usually people ask this question that FP32 has a very small epsilon error. And in fact, if you're just performing a multiplication, if you take the scale out, it's exactly the same as integer only. The problem is when you're performing quantization, there is a subtlety here, which is rounding operation. And this rounding operation can create order 1 error easily if you're doing simulated quantization and deploying it on integer only hardware. The reason for that is the rounding operation is not linear. The rounding of A plus B is not equal to rounded version of A plus rounded version of B. And a simple example of it is if you're doing this residual connection between these two values, 2.4 plus 1.3. If you first sum this up and then round it, you're going to get 4. But if you sum the rounded values, you're going to get 3, which creates an order 1 error. So many of these works that we're doing simulated quantization cannot be deployed on integer-only hardware because this rounding type operations, if there is an epsilon error in your simulation and what happens in hardware, you're going to get completely erroneous, wrong results for your deployment. And so we actually tested this. This is a result for ResNet 50. We just took the residual connection, not even the batch norm. Just take the residual connection and see how much effect will this rounding operation have when you're doing fake quantization and you're deploying it on an integer-only hardware such as NVIDIA's T4 GPU. So here, what we're reporting is the normalized difference between the activation that you get in your simulated results in PyTorch versus what you're seeing in hardware. So essentially, just look at the error between these two. And the x-axis is the different layers of ResNet 50. What you can see is that as we are going through the network, the error is increasing. For 8-bit precision, this increases to about 51% error between what you're getting in PyTorch and what you actually see in hardware. And if you go down to 4-bit precision, this goes to almost 100% error, just this simple integer operation. And why does it increase for 4-bit? Because order 1 error out of 256, which is for 8-bit, is much smaller than order 1 error out of 16. Because 4-bit, the lower precision, the more nuanced this becomes. And I highly recommend this book chapter by Goldberg, What Every Computer Scientist Should Know About Floating Point Arithmetic. A lot of interesting subtleties there. How can we solve this? Well, if we had a way of figuring out how to do the batch norm residual connection for accuracy, we can just perform all of these operations in integer arithmetic. There's no reason to, avoid it. Obviously, it leads to good accuracy results in your table, but you cannot deploy this on integer-only hardware. So let's actually see what we can do here if you're doing integer-only arithmetic. Well, we have the weights and activations in int4. Let's perform the multiplication in int4, and let's do the accumulation in int32. And when we're rescaling it back, do the scaling back also with integer arithmetic. This scaling back is essentially the multiplication of these. If you remember from what we had, we were basically multiplying these guys, wi4 and xi4. We were accumulating them in int32 precision, and we were scaling them with this factor to get the final result in 4-bit precision. The problem with integer only has always been that if you're quantizing the batch norm or residual connection, it leads to a lot of accuracy degradation. But we actually found a very easy fix for this. The easy fix compared to the previous state of the art from Google was that when you're doing fine tuning, so the process is the following: you quantize your neural network, and then you train it for a few more epochs, which is called quantization error training. You train it for a few more epochs so that your parameters can get adjusted. So you essentially have all the parameters quantized. You need to train it a little bit to recover the accuracy. And specifically for the batch norm parameters, if you quantize them from the beginning and compute the statistics with quantized values, we found that there is a big discrepancy because you cannot correctly capture the statistics of your activations. Instead, the fix is pretty easy. You just keep the batch norm in high precision so that you can first see what is the mean and standard deviation of my signal. I mean, there is no reason to compute that in low precision. You can compute that in floating point precision. But once you found the correct values, then you can quantize it, and you can keep it quantized forever afterwards for inference. And same thing for a couple of other things, such as nonlinear activation. So nonlinear activations is not in computer vision. Mostly people are using ReLU, but for natural language processing, we found that you can perform very simple, polynomial approximation to take that into account. So you can do any nonlinear activation with integer only as well. So with this, integer only actually works across the board. You don't need to worry about this floating point and these rounding operations and whatnot. And you're actually going to get very, very good state-of-the-art accuracy. So this is some results for image classification on ImageNet. MobileNet v2 is a compact, pretty compact model, very difficult to quantize this. The baseline model for MobileNet achieved 73% accuracy. This is the highest baseline for MobileNet v2. If you're not using the low baseline, this is the highest baseline. with 32-bit precision. It has a size of about 13 megabyte for the model parameters, and it requires a total bit operations of about 300 gigaops. And the top one accuracy is 73%. This is our work, Hawk V3, which is full integer only. It gets 73% accuracy, 0.02 degradation. And the model size is decreased by a factor of 4, and the total BOPs is reduced by a factor of about 15. And there is not even a single floating point operation in the entire Hawk V3. And we have actually verified that the error between what we have in PyTorch and what is in the hardware is 0. So bit for bit, everything matches exactly for the entire inference. We looked at ResNet 50. Here you can see that the baseline model gets 77.72% accuracy. Again, the highest baseline for ResNet 50. A model size of 97 megabyte in floating point precision. Hawk V3 achieves 77.58% accuracy, again, without any floating point logic, and the model size is reduced by a factor of 4. But the interesting thing is that there was a prior work from Jacob et al. From Google that had this integer-only paper where they got 74.90% accuracy with their integer-only paper. And the difference here is the treatment of residual connection on batch normalization. And the fix is pretty easy. Essentially, compute the batch norm statistics in high precision. Once you have them in high precision, then you do the quantization. Because there is no reason for you to not use high precision to capture the signal correctly first. And on Inception V3, the difference becomes about 4.5%. So for Inception V3, the baseline is 78%, and we're able to get 78.76%. So integer only works, and this is going to give you about 4x speed up when you're executing it compared to single precision. And it's not only computer vision. We actually published this work, iBERT, integer only BERT quantization. It's available online. It has been integrated with Hugging Face, where the idea here was that what about Gelu nonlinearity or softmax, which requires floating point logic, right? When you're performing Gelu, it requires you to either use sigmoid approximation, or you actually have to evaluate an error function integral, which requires floating point logic. But in fact, you can perform very simple polynomial approximations so that you don't use any floating point for BERT model as well. And here, interestingly, we found that when we are using iBERT, which is integer-only quantization of BERT model, on average, we actually gain in glue score compared to the floating point counterpart. So these are the different glue downstream tasks, MNLI, QQP, etc. And we found that on average, baseline Roberta base gets a glue score of 86, and iBERT actually gets 0.3 better. And what we're thinking is the reason for this is that iBERT overfits less for some of these downstream tasks, such as COLA, or for example, RT or MRPC, because these are pretty small. And same thing for Roberta Large. Actually, here we found that we get a 0.5 better improvement. And for the entire graph, there's not even a single floating point operation to perform inference. And we actually just last week open sourced this code and paper, which does integer-only quantization for automatic speech recognition. This is becoming pretty important these days because all the communication is online, and a lot of people who have, for example, hearing disabilities need to see what the teacher is saying. So, for example, Zoom has this integration. A lot of other companies are working on this. A lot of people are using this to detect sentiment of what the person is saying and so forth. And here you can get almost for free, you can get up to like 4x or 6x speed up for your automatic speech recognition with integer-only quantization. So these are two models from NVIDIA called QuartzNet and Jasper. Basically, they take audio signal, and the input is audio signal, and the output is what the person is saying. And the ImageNet version here is the Libri speech data, and they report this in word error rate, so lower is better. The baseline model in floating point precision is 3.80% word error rate. And when we do integer-only quantization, we get 3.92. And they have different versions, dev set and test set, etc. And actually for this quantization, we're not using any data. This is complete data-free zero-shot quantization. So we can actually push this to the limit when you're doing integer-only quantization. So basically the conclusion here is that now with the right way of treating the batch norm residual connection, you can perform integer-only quantization, and you can actually get the same accuracy as baseline, which is quite important for a lot of hardware companies that are creating a processor for the edge or processor for inference. They can have only what they need is very, very few floating point logic. They can essentially just use integer-only logic, which is quite important there. You can essentially pack 100x more logic with integer-only compared to floating point. But the big question here now is, okay, int8 works. Can we push this further to sub-int8 quantization? Well, obviously you can do that. So we can do, for example, 4-bit with NVIDIA RTX. But the problem here is that, consider a very simple ResNet 18 here. The problem is, if you use 4-bit for all the convolutions here, you're going to lose a lot of accuracy. So if you're using uniform 4-bit, some of these layers are pretty sensitive. Some of them are capturing, for example, edges in an image or different Gabor features in an image. And if you're doing those incorrectly, all the follow-on layers will also be incorrect, and there will be a big accuracy degradation. But the fix is pretty easy here. The fix is that keep as many layers at 4-bit precision as possible, but a few of the layers need higher precision. Because, for example, they're important Gabor feature detectors. We need to keep them at higher precision. Well, if we had a way of detecting that, we can keep those sensitive layers at high precision, and the rest of the layers at 4-bit will be good to go. But the problem here is that if we only have two choices for every convolution, whether you're using 4-bit or 8-bit, so every convolution is going to have two choices. This is going to lead to an exponentially large search space, 2 to the power of the number of convolutions that we have, which is quite hard to search through. So we need a way of determining this with precision systematically. Well, one of the things that people did in the literature was they used AutoML-based methods. They trained the reinforcement learning algorithm to figure out which layer should be 4-bit, which layer should be 8-bit. But I'm going to show that this is actually completely unnecessary. If you look at the model, you look at what's happening, you can actually determine that automatically. This is very similar to doing a Jenga game. In a Jenga game, you want to remove as many blocks as possible, but certain blocks are very sensitive. When you have a neural network, it's exactly the same. So basically in the neural network, what we want to do is we want to reduce the precision of as many layers as possible, but we don't want to make the neural net unstable. We don't want the output loss to change a lot. It's exactly the same as a Jenga game. In a Jenga game, if you're perturbing this block, it's going to lead to a lot of perturbation to your tower. So you would never remove this block. So it's the same as quantization. You don't want to reduce the precision of this block. But if you look at this block, I mean, this is pretty insensitive, right? You can remove this. And how do we detect this? Well, we probably poke it with our hands in different directions to see how much weight it's bearing. And schematically, that's going to give us a feeling of okay, this is a sensitive block. I shouldn't remove this. And you perturb another one and say, okay, this is not carrying a lot of load. Let me remove it. In a neural network, let's say you only had two different directions. So you had a convolution that only had two different directions. I can do the same thing. I can perturb the neural net convolution in two different directions. Compute how does the loss landscape look like. So I'm perturbing it in one direction. I'm looking at the loss landscape, perturbing it in another direction, and I'm essentially looking around and seeing what happens if I perturb this convolution. Is it going to break everything? Well, some of the layers will. So for example, this is one of the layers of inception that even the slightest, the z-axis is loss, even the slightest perturbation is going to lead to a lot of perturbation in the network. It's going to increase the loss a lot. So this means that this is a sensitive layer or a sensitive convolution. But on the other hand, if I perturb my convolution parameters in two different directions and nothing happened, that's like this Jenga block that's insensitive. I can either prune it or I can use low precision. So that's basically the idea of Hessian-aware quantization. We use low precision for layers that are insensitive, which corresponds to having a very flat loss landscape. And we use high precision for parameters or convolutions that are sensitive, which means that they have a sharp loss landscape. But obviously the neural net doesn't have just two directions. It has millions of directions, right? You can have a convolution that is of size, for example, 3 by 3 by 2000 in ResNet. It has basically about 10,000 directions. How can we quantify this? We can use the second derivative. That's essentially what quantifies this sharpness or flatness. We actually showed some theoretical results that was presented in NORIPS last year, where we showed that the right metric to look at is the average sharpness across all of the directions of your convolution. If I have the 2000 by 3 by 3 convolution, that means that I have about 12,000 different directions. I have to perturb the loss landscape across all these 12,000 directions, visually look at them and see if they're flat. Obviously, you cannot do that, right? Because that, I mean, that's impossible to do, right? But what we can do is we can look at the second derivative and we can compute the sum of the eigenvalues of the second derivative. And what that is going to give us is the average sharpness across all these 12,000 directions for one particular convolution. So the Hessian is essentially the second derivative. The first derivative gradient gives us the slope. Second derivative gives us the sharpness. So for example, if you look at y equals, for example, 10x squared, the first derivative is 20x. This is the gradient. The second derivative is 20. So this is essentially measuring the sharpness. For example, if I was looking at y equal 1000x squared, the second derivative will be 2000. So this is much, much sharper compared to the first one. We need to look at all the different directions. And the way to do this is to look at the sum of all of the eigenvalues of this second order derivative. And if this sum of the eigenvalues is essentially a trace, if this trace is very large, it means that I'm dealing with a very sharp loss landscape. And therefore, I need to use high precision. And if this trace is small, relatively small, that means that the loss landscape is flat and we're good to go. We can do 4-bit quantization. Any questions here? Okay, great. So let's actually.
Hi, Professor. I want to ask, what's the cost if I want to compute the Hessian matrix?
That's an excellent question. That's an excellent question. So the cost is actually pretty manageable. I have another slide on this. The cost is pretty manageable because there is a paper from Gholami, famous mathematician from Stanford. He has a 2007 paper. There's also a couple of papers from Yusuf Saad, where they show that you actually don't need to have all of this matrix and compute all of its eigenvalues to compute this trace. The trace is also equal to the sum of the diagonal elements of the matrix. So you give me any matrix that's positive semi-definite. I compute the sum of its diagonal values. It is equal to the sum of the eigenvalues. So I don't need to, there's no need for me to compute the eigenvalues. So that's the first identity. How do I compute this sum of the diagonal of the Hessian? There's no reason for you to form this matrix to compute its sum. There is another identity that Gholami and Yusuf Saad have a couple of papers that says if I have a matrix A, I haven't formed this. I don't know how it looks like. I can't access its diagonal. If I multiply this matrix A with a couple of random vectors, let's say I draw a random Gaussian vector Z, just Z equals rand np rand dot rand n, and this is going to give me a vector, and I multiply Z transpose. This is going to give me a scalar. Basically, I'm multiplying this matrix with random vector here and the projection here, and this gives me a single scalar. If I take the expectation of this, if I perform this multiple times, this is going to converge to the trace. What's the cost of this? The cost of this is about 100 backprops. So in PyTorch, you do 100 gradient backprops. That's the cost of computing this. And we actually have the code available online. I'll get to this, that you can run this on your laptop to compute what's the average sharpness of, for example, resonance. You can actually do this on your laptop. It doesn't require forming the second derivative. And that's the beauty of randomized linear algebra methods. And I'll get back to this, Yank, on another slide. So let's say we had this in our hands. We knew that, this is the Django tower we're dealing with. We know that this layer is sensitive. There's no reason to train a reinforcement learning to learn this. We know that we have computed the trace. We know that that's sensitive. Keep that at 8 precision. Let's see if that actually helps us. So this was, when we discussed this in our group, and people were always doubtful, right? This is nice theory, but does it actually work? In most cases, you have this theory, it's something that the practice doesn't work. But this is actually the cleanest result I've seen, where we didn't even do a single manual bit precision setting. Once we had the sensitivity, once we know which layers are sensitive, we keep them at 8-bit. There's not a single manual intervention in this process. And we said, okay, we showed the 8-bit results, right, for ResNet 50, 77.58%. What if the practitioner tells me, Amir, right now my latency is around, let's say, 240 millisecond. I need to reduce this. There's no way I can get this through. It needs to be 150 millisecond. Okay, we can give you that. You need to perform mixed precision quantization. So now your weights and activations are going to be a mixture of 4-bit and 8-bit. And what we're going to do is, based on the Hessian, we're going to automatically tell you which layers are sensitive. So you keep those at 8-bit precision, and the rest of them you can quantize with 4-bit. You can get a state-of-the-art accuracy of 76.73%. Everything is still integer only. We're not using even a single floating point, batch norm residual connection. And all of this was an exponentially large search space. Everything is fully automatic. So a human is not selecting the bit precision. This is fully automated. And we actually have results for other networks in the paper as well. But going back to Yang's question, what's the overhead? Yes, we are not searching, but there is this Hessian that you talked about. What's the overhead? Well, all of these calculations were performed on a 4 Titan RTX system. So we're not using Google scale or Facebook scale, resources. And in fact, all of the calculations, even for ImageNet runs, to compute the end-to-end bit precision selection takes less than an hour. And actually, we compared this timing with another state-of-the-art hardware-aware quantization, which uses AutoML to learn the bit precision setting for different layers. Essentially, this slide that we had here, it essentially trains the reinforcement learning to learn that, okay, the first layer is probably sensitive. You should keep that at 8-bit. Second layer, I'm not sure. Let's try 4-bit. Didn't work. Now let's try 8-bit, and so forth. And we actually compared with HAQ, and we found that these AutoML-based methods work very well if you have tuned their hyperparameters, but they're very sensitive. If the hyperparameter is not set correctly, it's pretty sensitive, and it's very difficult to find the right hyperparameter. So many papers report results on ResNet 50. So we first tested ResNet 50. And HAQ on ResNet 50 gets an accuracy of 75%, acceptable accuracy. It takes about 10 hours of search time, though. The AutoML takes about 10 hours of search time, whereas our approach requires less than half an hour for the end-to-end bit precision selection and gets better accuracy. And then we looked at other networks, such as Inception v3. So we played with a lot of hyperparameters. We tuned this a lot, actually. And HAQ, after 50 hours of search, the accuracy is only 71%. And we actually tried really hard to optimize this. And it's even it's using 32-bit for activation, whereas we're actually using 4-bit or 8-bit for activation. So it's actually, to some extent, it's actually an unfair comparison. And the end-to-end timing for us is 120 times faster. And we also tested this on SqueezeNext. HAQ gets 75% accuracy, we get 68, again, less than an hour. And everything here is fully automatic. And don't take my word for this. The code is available online, so you can actually test this yourself. Both the Hessian aware quantization framework as well as PyHessian, which performs the second derivative. And you can think about this, if you have the second derivative, we can do a lot of cool things with this. It can help us with our optimization algorithm. It can help us with a lot of trust region. We have a couple of papers on adversarial attacks and so forth. So, if you have a project that you think second derivative can help you, it's possible to do that with very little overhead, and we have the code available online. So in summary, quantization, and I'll just briefly describe pruning in 1 or 2 slides, depends really on the loss landscape. So there was a lot of papers when we were starting this that would tell you don't quantize the first layer, just quantize that layer and so forth. Well, this changes from one model to another model. What we really need to do is look at the loss landscape. If you have a loss landscape that's flat, that means that this layer is not very sensitive. You can reduce its precision. But if you have a loss landscape that's very sharp and rugged, that means that layer is very sensitive, and you don't want to quantize that. And again, once you have this, you can do a lot of interesting things. Pruning is a special case of quantization. Pruning is essentially removing a layer. That means that you're assigning 0 bits to it. So this exactly translates to pruning. So we have another paper which we put online last month, which is Hessian aware pruning. I'll briefly describe that. But you can go beyond the quantization and pruning. We had this paper at a Hessian, which achieves a state-of-the-art accuracy on NLP. It's an optimizer that uses this information. I have the gradient in SGD. Now I know the curvature as well. I can use that information to guide my step sizes. We had a paper for large batch training. It can essentially help you do large batch, and another paper that helps with adversarial attacks. And there's a couple of other works that people have been looking, that have been doing with this library. But let me briefly, in 5 minutes, describe pruning. So pruning, the goal is essentially just to remove the whole parameters. Don't worry about reducing the precision, completely remove them. So if you have, for example, an input activation here is shown in blue, and it's being convolved with different convolutions shown here. These are the different convolutions. Well, if I know which layers are insensitive, which convolutions are insensitive, I can completely remove them. And the output activation, I don't even need to worry about this last part. You know, it's also going to reduce the cost of applying the next convolutions. But again, the same question here. How are you going to determine the sensitivity? Well, second derivative, right? And this goes back to the 1990s paper from Yann LeCun, Optimal Brain Damage, where the idea was exactly the same thing. You look at the second derivative. If the second derivative is small, you completely remove it. So what Yann LeCun did in Optimal Brain Damage leads to unstructured sparsity, because it looks at one parameter at a time. If every single parameter inside the convolution has a small second derivative, you remove it. But that leads to unstructured sparsity, which is very difficult to speed up in hardware. What we said was, let's take Yann LeCun's method. Let's just apply this to layer-wise, convolution-wise or tensor-wise scale. So we said, let's look at the trace of an entire convolution, the trace of the second derivative. If it's small, which means that it has a flat loss landscape, let's completely remove it. And otherwise, we'll keep it. So this is the first extension of what Yann LeCun did. Tensor level, very fast, and it actually gets state-of-the-art accuracy when we're comparing it to other methods. But then what we found was that with structured sparsity methods, when you're removing it like this, when you're removing an entire tensor, it actually leads to a big irrecoverable accuracy loss. And this is an ongoing problem in the literature, that you see a lot of great papers in pruning. Most of them that don't lose accuracy are unstructured, which is, at least up to now, it's not possible to get speed up in hardware, unless it's a dedicated hardware. And then on the other hand, you see that papers that are doing structured sparsity, as soon as you remove, let's say 30%, 40% of the parameters, there's a big irrecoverable accuracy loss. So what we're proposing in this paper was the following. We said, where is the problem arising from? Well, you have a couple of layers that are completely insensitive. No worries, you can remove them. But as soon as you get to the 30% removal, 40% removal, there is going to be layers or convolution blocks that will have a couple of very sensitive parameters. We're looking at the trace, you're looking at the average sensitivity of the entire convolution parameters. But you can bet that there is going to be a couple of them that are going to be very sensitive. So what are we going to do for this? In structured pruning, you have to remove everything. So what we're proposing here is this idea of neural implant. So what we're doing is we're detecting which layers are rather sensitive, have these sensitive parameters inside them. And instead of completely removing them, we are replacing them with a neural implant, which is a low-rank approximation to this tensor. So for example, if you had a 3x3 convolution, instead of having a 3x3 convolution there, we are essentially replacing it with a low-rank 1x1 convolution. Or you can consider a CP decomposition. You can consider a spatial decomposition. All of those are possible. And the difference between prior low-rank approximation methods, we have a couple of works there as well, is we are detecting which layers to use this low rank through the second derivative. So this is essentially Hessian aware. So you're only putting an implant where it's needed. And this is actually getting very good results for structured pruning. I'll skip this slide in the interest of time. Basically, the idea is that Hessian aware pruning is the extension of optimal brain damage, which does this in a structured pruning manner. This is shown in red here. So here is a result on C410, resonant 56. Y-axis is accuracy, higher is better. And the x-axis is the percentage of remaining parameters. So the lower the x-axis, it means that you're pruning more parameters in your neural network. So you want to be to the left and to the top of this graph. The black line here is eigen damage from ICML19, which is another second derivative method. The red line is the Hessian ever pruning, and the blue curve here is the Hessian ever pruning with the implant, which, as you can see, gets better accuracy. So to summarize, for pruning, this is still an open problem. That structured sparsity, it's really good for hardware efficiency, but it leads to low accuracy. This neural implant idea can actually help you there. And unstructured sparsity, we get very good accuracy, but it's not efficient for hardware deployment. And we've actually tested this for a couple of other networks, like White ResNet 32. We found that the implant actually helps exceed even the baseline accuracy. ResNet 56 is what I showed you, and pre-ResNet 29, which is rather difficult, but this still works at relatively low pruning. So let me summarize. In summary, in the first half of the talk, we showed integer-only quantization is possible without any accuracy degradation for int8. This has important ramifications for people who are designing efficient hardware and efficient algorithms. You can actually close the accuracy gap degradation, about 5% higher accuracy compared to the previous state of the art from Google, which was basically the right treatment of batch norm for int8. And it actually works on compressed models, such as MobileNet. It works not just for computer vision. We've looked at automatic speech recognition and natural language processing with transformers in the iBird work. Then we discussed how you can push this further to sub-int8 quantization and still keep integer only. Don't do binarized neural network and then add a residual connection in floating point precision. No, everything is integer only. So actually you will see the speed up, but still it's possible. You can do sub-int8 quantization without any reinforcement learning through HawkV3. And the key idea here was to detect which layers are sensitive. It's like the Jenga game. Which layers are sensitive, which blocks are sensitive, keep those at high precision. Otherwise, you can quantize them. And in our collaboration with Amazon, we actually deployed this in hardware, and we verified all of the results that I showed here today. So these are not simulated results. And we've actually recorded 50% speed up with the mixed precision in4 and int8 quantization. Thanks so much for your attention. The code is available online, and if there was any questions and anything that was not clear, please feel free to ask now, or if you're watching online, please feel free to email me. Thanks so much.
Thank you, Amir. Thank you for your very wonderful talk. So any questions from the audience?
So I have a quick question. Thanks, Amir, for the great talk. Actually, I learned a lot. So regarding the quantization, you at some point mentioned it briefly, but I was wondering the impact of the quantization on the model robustness in general. So can you elaborate on that part a bit, please?
That's a very good question, Salman. That's an excellent question. I think there is a couple of hypotheses out there. We're also testing something here that some of the work in the literature have shown that when you're doing quantization, you're actually more robust. Let me become a little bit technical because we're working on this. Some people in neuroscience say that our brain stores information in quantized. I'm not an expert in neuroscience, so please take this with a big grain of salt. Some people say that our brain is storing memory in quantized format because it's more robust to noise. Because continuous signal is like analog signal, right? Any thermal noise is immediately going to pollute the signal. But we never forget our home address. We never forget our names. We never forget our date of birth. And a lot of the neurologists, going back to the 1940s, say that the human brain is using discretized, quantized format to store information because it's more robust to noise. So that's one way of looking at robustness. I'm not an expert in that, but there was actually a paper last year, a very well-cited paper that had a big result here. That's one way of robustness to noise. That's why digital is, for example, always more robust than analog. There's another robustness, which is to adversarial attack. There is a paper that shows that when you're doing quantization, you can get more robustness. Some people have shown that that's not always the case. I think that's because adversarial robustness is still an unresolved problem. People have results that show that the non-robustness comes because of problems in your data, not just the model. So that's an active area. One thing that we are looking at is, in the iBird paper, let me go to the iBird paper. Again, take this is still open research, so the results are not certain. But one of the things that we found is that when you have quantized values, you're not able to overfit to small regions where you have a very small loss, right? For example, let's say Professor Nosebal has a good graph for this. Let's say your loss landscape looks like something like this. Just imagine, just you had these points that had low loss values, these local minimums, right? If I was optimizing an infinitely small point, I can always get stuck here, right? If my x-axis, I could use any floating point value, I can always get stuck here. But when I do quantized optimization, it's as if I'm instead of having an infinitesimal small point, I have a point that's has a diameter. For example, for 8-bit, this is the diameter of my ball. There's no way that I can actually get stuck here. It just doesn't, the loss, I cannot represent that. So these points actually are completely blind for me. And for iBird, we found that this is actually one of the reasons that iBird gets higher glue score is because it doesn't overfit as easily. But this is, again, these are still open problems. So that's another angle. But this is an open problem, Saman. So
it makes perfect sense. Yeah. Thank you. Yeah, that sure. Clarifies it. Thanks.
Sure.
Any other questions?
I have a question. For your pruning part, so you say you can use the low rank approximation to replace the layer, which is less sensitive. So is there any connection between the low rank property and the sensitivity? So I mean, why you can use low rank approximation to replace this layer? Well, what if this layer is with 4 rank? So how? I mean, I want to know, is there any connection?
Yes. That's a very good question. So all of these layers are actually full rank. So if you looked at this way back in time, without Hessian, right? All of these neural net, actually, if you look at the CP decomposition, or even if you project this into a 2D matrix and you look at the rank, it's actually full rank. So if you're looking at the SVD, it actually, you see a full rank. So that's why, when even back in the day when we were looking at this, it was not working because, we were cutting, for example, 50% of the, of the signal, right? 50% of the rank, and the accuracy was pretty low. So if you look at this individual layer, it's okay. So, what we were missing back in the day was the following. So when you do low rank decomposition, right, what do? You say, I have a matrix W. I want the low rank approximation to this, and I want this error to be small, right? I want as close as possible to this W, but I want to use low rank, right? If this was like this, I want to only use this low rank, and I want this error to be small. This is not what we really want in a neural net. Because in the neural net, you have many of these layers back to back, right? You have a lot of layers, and you really actually don't care if this is not close to the original W. What you care is that this output is not changing. And that's what we were missing back in the day, like 3-4 years ago that I was looking at this problem. We don't actually, it's okay. If the W is not the same, that's completely fine. If the output is still flat, that's okay, because these other W's could actually, help you recover the accuracy. So here, the idea of the low rank, the way we were looking at it, and I believe what you're referring to is not to have a low rank that's close to W, but to have a low rank that wouldn't cause a big output change, a big increase in your loss function. And how do we determine that? Essentially, the second derivative again. If you have a second derivative that's relatively sharp, that means that this layer is somewhat sensitive. So you're going to use a high rank decomposition, let's say. If it's completely insensitive, you can completely remove it, put rank 0. That's basically the idea. We didn't do this in this paper, but you can imagine that, if you had more sensitive, as a layer that was more sensitive, you can use a CP decomposition, or you can use spatial decomposition, which would be basically a 1x3 and a 3x1, a 3x1 and a 1x3 convolution. And still, you're saving 3 parameters, right? You're saving 3 parameters per convolution and also flops. So the degree of rank, you can change it. So I think that's the difference. Also, for quantization, there has been a lot of works starting from Shannon in digital signal processing is all about this. How can we reduce the bit precision as much as possible? What they were looking at was, I have this signal, I need to match just this signal. But what's different in neural net quantization compared to the classical literature is that it's okay if the signal is not the same. As long as the output signal is not perturbed, that's okay. And so many of the quantization works that you see in the literature, that's the difference with classical works.
Okay, thank you so much.
Any other questions? Yeah, so if the audience don't have questions, so I would like to ask a question. So like the idea of the using the Hessian, the second order method, I think it's a very general criterion as you just described. So it can be used for the quantization, for the pruning, and also for the low rank decomposition. Yeah. So I think in your slides, I noticed that you also as mentioned that so maybe it can be applied to the efficient training. So how do you view the perspective of that? So I remember that I think last year or 2 years ago, so there's some paper from the Princeton, they also investigated that. So how to efficiently to implement the second order optimization based the faster training on the distributed cluster. So how do you think about it? So is there still some of the current emerging challenges that we need to overcome towards this very attractive goal?
Yes, that's an excellent question. We had a paper on this at Hessian, which is actually the code is also available online here. So this is essentially the idea there, that you're doing efficient second order optimization. So the idea here is exactly the same as what I was describing. The difference here is that you're not quantizing now. You're essentially, you have a point here that you're trying to optimize to get to this point, right? If I had the second there, what do we do in gradient descent? We look at the gradient and we say, okay, the gradient direction is here. I go in the negative direction of the gradient, I get here. Then now, the gradient is this, I go here and so forth. Second derivative is giving us the curvature. So what the second derivative at here tells me is that, look, the loss landscape looks like this. So immediately I know that, okay, I need to go here. So essentially it tells me where to go. The Newton's method immediately tells me where to go. So one of the things that we thought about was that, okay, actually, can we use this information when we're doing the optimization? And the way to do this is again, using the trace, look at the sharpness, get an approximation, and then go along that direction. That's one way of doing it. The other thing to do here, the other thing that we thought about was that, when you have loss landscape like this, that has very rugged loss landscape, right? You don't want to get, you want to basically take small steps because the loss landscape is pretty rugged. How do we measure this against second derivative? So one very simple idea in Ada Hessian is that, if your second derivative is too large, take small steps. If your second derivative is too small or relatively flat, take much larger steps. And you can actually do this very efficiently. So we have actually even trained large NLP models with this idea of Ada Hessian, and we were able to beat the state of the art by quite a large margin. And the code for this is also available online. It's part of PyTorch Optimizer. You can actually try this for yourself. Just download PyTorch Optimizer and use Ada Hessian and see if you get better results. But there is a lot more to do here. What we did here was, I would say, like the first step here, which was we were just looking at the trace and just changing the step size. You can do a lot more with this. And I think this is an emerging trend. One thing we found here was that even if your learning rate is 20x off, so your learning rate, you don't have your 0.1 learning rate figured out, it's even 20x different, and still you converge to very good accuracy. And so this can save a lot of training. But one problem with second order derivatives is that the cost of computing it is very little, but the memory overhead is about 2 to 3x the SGD. So for example, when you're training GPT-3, you cannot use this, at least not now, because 3x higher memory is okay for ResNet, it's okay maybe for even BERT model, but it's not okay for GPT-3 scale because every bit of memory matters there. So one of the works that we are following right now is to reduce the overhead from 3x down to comparable, maybe 1.5x of SGD using checkpointing.
Okay, so you mean that, so in your method even for the training, so you still don't need to calculate explicitly for the Hessian matrix itself. Exactly. Yeah, exactly. To inverse itself, right?
Exactly. Yeah. I never. Yes, we never do the inverse. So basically, what we do, we know that the second, the backprop. Basically, maybe I can in maybe 2 minutes explain what we're doing. Basically, a second derivative Hessian is essentially the second derivative of our loss function with respect to our parameters, let's say. which is essentially the derivative with respect to gradient. So the way that these matrix-free methods work is that, if I'm multiplying this Hessian with a random vector and I'm multiplying the transpose, I can get the trace, right? So we showed that. But the big question is, how do I multiply this Hessian with a vector without forming the Hessian, right? So the way to do this is that, the derivative with respect to W of G times V, right? This is exactly equal. There's an equality here of the derivative. I can bring the V inside. This is exactly equal to this. Why? Because this is equal to derivative of G with respect to V times V with respect to W times V plus the derivative of V with respect to W times G. This is 0 because this V was irrelevant, right? This was a random vector. So there we have this identity. And in PyTorch or TensorFlow, what you need to do is basically just multiply your G, just compute the dot product between your G and the vector V, and just do another backprop. So the cost of all of these H times this matrix, this big matrix, the H times Z is only another backprop. So the computational cost is not quadratic. And once you have this, you can multiply it to anything, right? You can to compute Z transpose HZ, compute the expectation that gives you the trace. You can even compute low rank decomposition. In PyHessian, we can actually give you even the full eigenspectrum, can show you the full eigenspectrum, of how does the eigenvalues look like with manageable runtime. And we actually found, for example, what happens when you have batch norm, what happens when you have residual connection. This paper, for example, from Lee et al., that they showed that residual connection makes the loss landscape smoother. You can actually quantify that by using Lancho's algorithm, again, with a couple of 5-10 minutes, not hours.
Thank you. I think it's a very elegant idea.
Thank you. Yeah, and the code is available online. People can actually try this. So don't take my word for it. You can actually verify it.
Okay, thank you. So any other questions from the audience?
I just had one small question. Yes, it's just when you talk about large Hessian and small Hessian, I was wondering, how do you basically make that decision? Is there any scale involved? If you know what I mean? I mean, what is too large, what is too small? How do you make that decision?
That's an excellent question. So there is no absolute value here. It's only relative. So relative to the other layers, what's the relative magnitude of the Hessian? Because in absolute, the reason it doesn't have a meaning is because, for example, I can have y equal x squared, right? And then I can do change of variables, right? For example, say that, if x was 10z, then y will be equal to 100 times z squared. So is this now sharp or is it small, right? So all we're doing is basically relative. So this block relative to that block, what's the difference? That's how we're sorting these blocks.
Oh, so when you want to make that decision on using lower precision for which blocks, you're basically just basically comparing different layers and choosing a percentage.
Exactly. Yeah, that's an excellent question.
Okay, that makes sense. Thank you very much.
Sure.
Okay. Any other questions? Okay, so if no more questions, so again, thank you so much, Amir, for this wonderful talk. So at least for me, I learned a lot. Yeah.
Thanks for having me. It was a pleasure.
Yeah. Okay, thank you. So, okay, also thank everyone for attending this week's talk. So see you next week.
Thanks, Bob. Bye, everyone.
Bye, everyone.
Thank you.